Hi, everybody, and welcome to Echo Live. Today we have a very exciting program planned for you, and you might notice that I'm standing somewhere kind of new. You might recognize this space from a past episode of Echo Live when I showed you that Mentos and Coke geyser. We're going to do some demonstrations that maybe aren't such a good idea to do in my basement studio today, because today we are talking all about rocket science. This is an episode that you have requested. You guys have asked for rocket scientists and rocket science, and so I'm here to deliver. I've got quite a few different rockets that we're going to launch all together today. I can see lots of friends starting to join in on Zoom, in Facebook, and on our YouTube Live. So if you haven't done so already, go ahead and introduce yourself in the chat feature. You can use that to answer questions, to ask questions, and to make suggestions for some of our rocket science experiments that we're going to show you today. So it's going to be a really exciting episode, and let's get started by talking about the physics behind rockets. Now, the main principle involved in any rocket launch comes from Newton's third law. This is something we've discussed on Echo Live in the past. Newton was an amazing physicist who lived a very long time ago, but his laws are still heavily involved in all the science we use to launch rockets, including the ones that NASA and SpaceX just launched only recently. So let's take a look at a diagram that kind of describes Newton's third law to us. Now, we are pretty familiar with Newton's third law, that it tells us that for every action, there is an equal and opposite reaction. In a rocket, that's pretty simple, right? When we launch a rocket by generating some sort of thrust, there is a force that pushes down on the surface of the Earth. The opposite reaction, right, comes when that push goes back on the rocket and sends it flying into the air, high above Earth's surface and even into Earth's orbit and beyond. So remember that the action is our thrust, and the reaction is our lift from our rocket off the ground. So I have it in both orientations here because we don't normally launch rockets horizontally. That could be incredibly dangerous, right? Normally, we launch rockets from the ground vertically. So the action pushes down, and our rocket, therefore, pushes up. Now, let's take a look at that in a demo that we've tried before on Echo Live, but this is one of my very favorite science demonstrations to demonstrate Newton's third law, because it's one that you can easily and safely try at home with some really, really simple materials. So let's take a look. This one is our Alka-Seltzer Rockets. So let's get a closer look at some of our materials here. So we might be familiar with this demonstration, right? We know that all we need for our Alka-Seltzer Rockets are some of these little white containers. Does anyone remember what we called these little white containers? Maybe not something we see very often anymore, kind of an obsolete object, but this is what we're going to use as our rocket itself. The fuel to put inside our rocket is going to be a combination of H2O, handy dandy water, and then some Alka-Seltzer tablets, which is going to generate a gas and build pressure inside our, you guessed it, film canister. So if you're not familiar with a film canister, ask an adult in your life if they have any old film canisters laying around, because we really don't use these for film anymore. Most of our cameras now are digital, and we can store everything right on a chip and put it into our computer. But long time ago, not really, we used to put our film in these, take them to the store and develop that film. Since we don't need it anymore, now you can use it as a pretty cool science tool, because what's cooler than rockets? So let's go ahead. The first step in our Alka-Seltzer rocket activity is filling our containers about halfway full with water. We need the water in order to dissolve our Alka-Seltzer. We've talked about Alka-Seltzer in the past, that Alka-Seltzer contains both an acid and a base. And when the water dissolves those two compounds, we have a highly reactive acid-base reaction. It generates a lot of carbon dioxide gas, and carbon dioxide gas takes up way more space than the solid Alka-Seltzer tablet does, this little white solid disc. As that takes up more space and we trap that expanding gas inside our closed container, right, that builds pressure. Eventually, the pressure will become too much for our Alka-Seltzer rocket to handle. It will pop the lid off, pushing down on the Earth and having an equal and opposite reaction by throwing the film canister way up high in the sky. Now, normally we don't get a pretty good look at just how high these rockets can go. So I'm going to zoom out just a little bit. Of course, safety first always when we're talking about rockets, right? So I'm going to go ahead, put on my safety goggles here. Safety goggles are here to protect my eyes just in case, right? Since we're standing pretty close to our rocket that's going off today, we're going to take 1/2 of our Alka-Seltzer tablet, drop it in each of our containers, seal the lid, flip them upside down. Woo, that one went off already. All right, let's see if we get our next Alka-Seltzer rocket to go. There it went, and oh, I almost caught it, right? Let's try that one more time. So let's go back over the physics of this as it relates to rocket scientists. Rockets, right? This is all about Newton's laws. We are creating our force downward on the Earth, which generates an equal and opposite reaction, throwing the film canister up into the air. Set this one up one more time here. Drop in our Alka-Seltzer to be used as our fuel. Seal our lid, flip it on its end, and the pressure is building. Oh, just a lame little one there. But the principle that's going on here inside these rocket reactions is the same, no matter what kind of rocket you are talking about. But these rockets would be horrible if we were using these for space travel or any other kind of official use, because they're not very stable. You might have noticed that they were pretty unpredictable. They flew in really any direction that the table pushed them, right? And they had no way to stabilize their flight. So these didn't make for really great rockets because they were lacking some really important pieces of any rocket. And so let's take a moment and talk about rocket anatomy. So let's pull back up our slides here. Even if we look at these rockets right here on our Newton's third law slide, these rockets have some pieces to them, right? It's not just a cylinder like our film canister. We've got a few other pieces. Now, does anyone know a piece of rocket anatomy? Could you name any of the pieces of these rockets? If you're familiar with what we might call any of the pieces of these rockets, go ahead and tell me in the chat. I'll keep an eye on your answers here. So what I'm looking for are, can you name things like, what might we call, this pointy part at the front? What might we call these devices right on towards the bottom of our rocket? You can name me anything. So if you're kind of familiar with rockets, you might know lots of people telling us that these are really common among most rockets. This pointy piece at the front is called our nose cone, and the pointed ends towards the bottom of our rocket, that's what we call the fins. Now, every piece of a rocket has a job. The nose cone, that pointed part at the top of our rocket, is there to reduce drag. Drag is the force that rockets experience when they're pushing through the air, right? Since we have an atmosphere here on Earth, there's a lot of air pushing back on our rocket that's trying to resist that rocket from being lifted off the ground. The nose cone being pointed like that helps the rocket to cut through the air and reduce that backwards push on the rocket of drag. Now, if we go through the other parts of this, right, this section right here is what we might call the payload section. If this model rocket were carrying astronauts into outer space, that's where our crew might sit. That might also be where we place the cargo if we were sending up supplies to the International Space Station or perhaps other places up in Earth orbit. Then inside the body tube, we've got a couple really important pieces. Now, since this is a model rocket, this one has a recovery system, which you might be able to tell is a bunched up parachute. So recovery just means that's our way of getting this rocket back, safely back down to Earth once it's done carrying our payload up into the air. We also have our recovery wadding, which is there to protect the parachute, since at the bottom of our rocket, we have an engine. And most rocket engines, right, utilize combustion. Since a combustion reaction gets very, very hot, that recovery wadding is there to protect the parachute from being burned, so it's not damaged at that initial launch. Then the fins down here on the bottom, those are probably the most important external piece of the anatomy of this rocket. The fins are there to stabilize it. The fins are going to help keep the rocket steering straight instead of getting up in the air. And since it's going to travel pretty fast, if the fins weren't there, it might wobble and start traveling in any direction that the wind takes it. So the fins are there to help recover or to help stabilize it. And then of course the engine mount is just our way of placing the engine inside our model rocket. So we have a fun activity that you can try at home, because we might not all have model rockets just laying around, but anyone can make another really simple type of rocket to practice designing rocket anatomy. So I've got some really simple materials down here on my table. Zoom in for you. I have what I call here, this is a piece of foam insulation, but you could also take a piece of a pool noodle and just chop it really short, just like this, so that you can start attaching some of those other pieces to our rocket. Now, instead of using an engine, since engines can be pretty dangerous, we're actually going to use an elastic launch system. So this is one where I've just taped my rubber band across the top of our foam insulation or your piece of pool noodle, and then you can actually just pull back. See if I can get a little bit more zoomed out look. Sorry, I'm standing a little further away from my camera than I might normally. There we go. All you'll do is pull back on your rocket, build up that potential energy, which we love to talk about here on Echo Live. Build up that potential energy by stretching the rubber band and release, converting it to kinetic energy. But you might not have seen where that rocket went because it just kind of went crazy, right? We didn't have those fins to help stabilize our flight. But using these materials down here on my table, we can add fins. So all I did before the program is I just cut the bottom of my pool noodle so that I can slide fins in between these different slots here. And I even pre-cut some. So cardstock or some kind of firm paper or cardboard works really great for this activity. And all you'll do is just slide in your fins one by one. And you can experiment with this activity and make it a real experiment, right? By changing variables like using more or less fins, or you could change the shape. You'll see that I used these triangular fins here because that's usually what I see on rockets, but that doesn't mean that this is the only way to build a rocket, right? You could make them whatever shape you want and do a test and see which designs work best. To attach your rubber band, duct tape works really, really well because it's pretty sticky and it's not gonna fall off once you stretch your rubber band really, really tightly. So all you do is lay your rubber band across the top of your foam insulation. You're gonna tape across your rocket, pull your rubber band up so that it's not trapped under your tape. You can see that I now have the rubber band just hanging there. And then I like to take the other piece of tape and secure it all together. So just wrap it all the way around your rocket, maybe near your payload section. But again, you can experiment by changing different variables or changing different elements of your rocket to see how well this launches. So now we can take this one. Let's go ahead and zoom back out if my camera will cooperate with me. Ta-da! All right, now that we've attached some fins for stabilization, let's see if we can steer our rocket just a little bit better. We're pulling back, converting that potential energy into kinetic in 3, 2, 1. And we had a bit of a malfunction. My fins came right off my rocket there. But again, you can really easily create these rockets at home. They're really, really simple, inexpensive materials. And that's going to help you to understand why we're constantly changing rocket designs. We're constantly improving them, changing the shape of our nose cones or our fins, using different amounts of heights and weights. Because right now, one of our biggest challenges is just how expensive it is to send rockets into space. For every pound of cargo that you're trying to carry, it costs about $10,000 to lift that 1 pound off the ground and get it into Earth orbit. So rocket science is one of those really important fields in the world right now because everyone is trying to move to space, get more satellites out there, help our astronauts to get back to the moon and even further on to Mars very, very soon. All right, now I have a couple other big rockets here. These ones came pre-designed. This one I purchased at the store because we don't have to use a combustion reaction in order to fuel a rocket, right? All we need is something that's going to generate a force, and we can actually use air pressure to do that. We did it once already with our Alka-Seltzer rockets. That was air pressure building up inside our container, storing that pressure until it was instantaneously released, throwing our cylinder into the air. Now with this, right, the air is trapped right here inside this tube. So we are limited by the volume of air that we can fit just inside this one tube. Now, I'm gonna do 2 experiments with this rocket. And I want us to notice the difference. So let's see. This is the maximum amount of air that I can fill inside this tube. And when I pull down on this orange piece, our rocket is going to launch. So let's do trial number 1, and then we'll follow up with trial number 2. And I want you to tell me what is the big difference. Ready? Trial number 1 in 3, 2, 1. All right, trial number 2. Now, we're going to load the same amount of air. Like we said, we are limited by the volume here. This is the farthest I can pull our rocket tube apart. Our tube is full of air. And let's try trial number 2. I'm going to take a couple steps back and tell me, what do you notice? What'd you think of that? What was the big difference between those 2 reactions? It can't be the amount of air, right? Because we said that is standard. The volume of air is the same, but what was different between my 2 trials? Tell me what you think. Keep an eye on the chat. Tell me what you guys think. What did you notice between my 2 trials? Did one work better than the other? Yeah, Helena tells me I pushed it differently. So if I had to replicate that, right, trial number 1 probably looked something like this. And trial number 2 looked something like this. Big difference, right? There was also a difference in how far my rocket traveled, right? In my first trial, the rocket traveled maybe less than 3 feet away from our launch site, right? Even though we were using the same amount or volume of air to power it, right? But by pushing it differently, right, it had a much greater pressure. So when I pushed down very, very quickly, I pressurized that air. And so the volume of air was the same, but the pressure was very, very different. Now we've got a couple more larger scale experiments that we're going to try here on this episode of Echo Live. Now, you might have noticed that set up to the side of me, I have another rocket. This one right off here, this is also an air-powered rocket. This air-powered rocket is powered by pumping the canister full of air. The number of pumps, right, changes the pressure within the container. The volume stays the same. The container is the same size no matter what, but by forcing more molecules of air into that same amount of space, right, we build up more pressure. So with this rocket, let's do 2 more trials. We'll do 1 trial with just 2 pumps of air, and then we'll do another trial with 10 pumps of air. And I want you to notice the big difference between these 2 demonstrations. Let's go ahead and try. All right, trial number 1, 2 pumps of air. 1, 2. Blast off in 3, 2, 1. All right, so we had liftoff, right? We did have enough thrust to carry the weight of the rocket up into the air. So we had enough force to defy gravity at least, but only by a little. Now let's try that again. And we said we're going to increase the pressure this time. Instead of 2 pumps of air into that container, we are going to do 10 pumps of air. That's much more pressure inside the same amount of space, which should, in theory, create a larger force of thrust on our rocket. So let's go ahead and give that a try. Wrong side. All right, our rocket is loaded on the launch pad. We're gonna give this one 10 pumps of air. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's go ahead, release that pressure. We'll have blast off in 3, 2, 1. Not quite. Oh, just barely into our lake just behind me here. But you'll notice that my backyard makes a pretty good launch pad. Now, you might notice that when we launch rockets from US soil, at least, we normally launch them from places like Florida at Cape Canaveral or from the Kennedy Space Center. That's for a reason, right? We want an area for our rocket to come down and land safely. So you got it, Steve. The rocket did make it into the water by design, right? It's a safe place for a rocket to come down, lots of open space, nothing for it to hit. But this is why we launch rockets normally in real life out near the water as well. Now, we've got a couple more rockets to show off here, and these ones are a bit more exciting. We're going to launch off 2 different model rockets. So I've got an example model rocket here, and let's go back through the anatomy of this rocket together. Zoom in. There we go. All right, so this model rocket has all of those components that we talked about in that diagram, right? We've got our nose cone up top, this pointy piece, which is there to reduce the force of drag. It's very long and narrow. It's a pretty good design for a rocket, right? You might notice that it looks pretty similar to the ones that we really do launch into outer space with astronauts. This section here is what we call the payload, right? Inside the payload, we do have our recovery system. So if I take off our nose cone and I just gently pull everything out, packed in there pretty tightly because we don't want it to come apart on launch, but if we just pull gently, I can actually pull out our recovery system, which we said in most model rockets is a parachute, right? So when this rocket ignites, right, it will get high enough into the sky that that load will blow this parachute out into the air, and it will help this to safely travel back down to Earth. We also have our fins on the end. These are going to help to stabilize the flight of our model rocket once we launch it. And then in the very bottom is the most important piece. Down here in the very bottom of our model rocket is where we insert the engine. Now, most model rockets utilize a solid fuel. So this solid fuel gets slid right into the bottom of our rocket, and then it's ignited using a long fuse. See if I can pull it to the side. There we go. So it fits right in there, and then it gets ignited with a long fuse. It goes off in a couple stages. So one is going to throw it above the ground, one is going to leave a smoke trail, and then the last one is going to pop, which should help to deploy our recovery system. Now, unfortunately, we're not going to launch this rocket today, right? Because packing the parachute in there very, very carefully and safely is the only way that we can guarantee that it works. But don't worry, I have a couple more model rockets, and these ones both look kind of different. Now, the 2 rockets we're going to launch today are right here, and they look really different from one another, right? We've got this kind of funky looking one, which is the first one that we'll launch. And you'll notice that this one isn't very long, and it doesn't necessarily have a payload chamber. So this one doesn't have a payload because instead of holding a parachute as a recovery system, this one is shaped like this, almost like a wind turbine or a windmill, because as this travels up in the air and back down, it should fall like a helicopter off of a tree and help to slow it down on its way back down to Earth. So instead of a parachute, this one utilizes a payload or a recovery system that's actually built into its design with these kind of funny looking fins. And then the other one we'll launch is a classic. This one and this one are exactly the same. We're not going to take the recovery system out because we said it's packed in there really, really carefully. We don't want to damage it. We don't want to disrupt the parachute packing the way it is. But I'll show off where we're going to launch from next. So if we take an up close look at the back of my yard, you'll notice this little red thing with a long tube coming off it. We said that that tube or that tiny little metal rod is there to help stabilize our rocket. Man, I wish my camera would cooperate today. There it goes. So that's going to help stabilize it for just that first 2.5 or 3 feet of flight. That way the rocket has direction as it lifts off the Earth, and these rockets are going to travel very differently from one another. So I'm going to head over there towards the back. I'll try to give you a really loud countdown. Hopefully you'll be able to hear it. I'm not quite sure if the range of my microphone will quite do it today, but I'll definitely hold up my fingers as well, give you a 3, 2, 1, blast off, and then you'll know it's time to launch our first rocket. So let's go ahead and pan our camera up just a little bit. I think my remote is getting hot. There we go. Perfect. All right, I'm gonna head over there and we'll grab our first rocket. This one has the built-in payload system right in its design. So no parachute on this first rocket. We're sliding it down our launch pad, and it's sitting nice on there, really, really flat. And then we just have to attach our fuse because you would never want to launch a rocket this close range. It is a combustion reaction. We said we're utilizing a solid fuel here, and so that could be very dangerous. We're just going to go ahead and hook up our leads. And now everything is set to go. And as soon as we push the button and ignite our solid fuel, we should have liftoff. So pay very close attention. We are going to go ahead and launch our first model rocket in 3, 2, 1, blast off. In the water too. So didn't travel extremely high by any means. So let's think about that design, right? That one looked a little different than our first example of a model rocket. The nose cone on that one was really small, much narrower than the design of the rocket. Oh, good, you guys could hear me. That's so good. I'm so glad you guys can hear me, even from that far away. So this rocket, right, has a really pointy nose cone and a really narrow design, and that's to help reduce the force of drag that's pulling back down on the rocket. So even though the design of that one was there to help recover it, was there to help slow it down on the way back down to Earth, it also slowed it down on its way up. There was way too much air pressure pushing down or dragging on that rocket for it to be very, very efficient. So probably why we don't see many rockets designed like that one, but we do see a lot of them designed like this one and my silver one. So that's the one we're gonna launch next. Let's see, that one's gonna go pretty high. So I'm trying to decide, how about you guys let me know in the chat, would you rather watch our rocket launch from the ground, or would you rather have this view? Oh, not that view, this one. Would you rather look up in the sky and try to see where it goes up in the air? I'll let you guys decide. Take just a moment. I'm gonna go hook everything up and I'll come back here and check in just a second. So tell me, would you rather watch liftoff from the ground, or would you rather, ooh, my camera doesn't want to change. There we go. Tell me, liftoff from the ground or recovery from the air. We might not get a fantastic view of either, but I'll let you pick. I'm just going to go set up our leads just like last time. I won't launch it just yet. I'll let you guys tell me what you think. All right, our leads are on. Just make sure everything is set and ready to go. Let me come check what you guys said. So you can either get this view where you can see it launch off the ground, which is gonna be pretty cool. Let's see. Oh, we're getting votes for both, up in the sky. All right, let's try our launch from up in the sky. Let's see if we can catch it. I'm hoping that you guys will get to see just how far this one travels, because this one is much more aerodynamic. The shape of this rocket is much better designed to help lift that rocket off the ground with very, very little air pressure, slowing it down. And this one also has a much larger engine in it, much, much larger. And so this one could travel up to 650 feet in the air, depending on wind conditions, which right now we're actually at a great spot, not getting too much crosswinds. All right, let's see. So we have our camera panned all the way up. Let's see if we can get a good view of this. Now you can't see me launching, but hopefully you can hear me. Steve told me he got a good, he could hear me just fine last time. So let's go ahead. We are launching in 3, 2, 1, blast off. I'm not sure if we saw anything, but we did get parachute deployment. We got parachute deployment. We could actually see it land safely in the lake at a very, very slow pace. And so it's actually floating around right behind me. Now, thankfully, I have some pretty fantastic neighbors who I'm calling my recovery team today, and they're gonna help me go grab the rockets that we have lost in the lake so far. So don't worry, I am gonna go grab them. Unfortunately, our silver one is made out of some cardboard, and so it's probably not relaunchable, but our other ones are. That first silver one that we launched with the funny looking fins, that one is recoverable. We can launch that one again just by putting in a brand new engine. This one is as well, if we were to launch this one, which we could do another time here at Echo Live. So if you all have any questions, let me know in the chat. We'll take some time to answer those before we head out today. But we'll talk about recovery while we wait for those questions to come in. Now, this is an example of SpaceX's rockets, and they, instead of using a parachute recovery system, they have their own design where they are actually landing rockets back on a floating platform in the middle of the ocean. So nice and far away from anywhere where people might be. That's for safety, but we can actually reuse these rockets. So instead of letting them splash down in the ocean where we could have lots of damage, they've actually designed engines that will help safely land and steer these rockets to land safely on these platforms floating in the ocean. So if you have any questions, again, let me know in the chat. We are very thankful to be able to bring these programs to you for free every weekday at 2:30 p.m. But we are also looking for your feedback. So we posted a survey on our last 2 Echo Live videos to have you guys give us your feedback about what you've thought about Echo Live so far. If you fill out the survey, you can enter also to win a free week of My Size Spark Camp, which is entirely virtual. Even if you don't live in Michigan, even if you don't live anywhere near the Science Center, you can still come to summer camp with us virtually. I'll be there. Some other Michigan Science Center educators are going to be there. We are going to teach you fun experiments in real time on camera so that we can do things together. Fill out the survey. We'll post a description in the link to this video again as well. And if you're looking for more information about those camps, of course, you can visit our website as well. So let's go ahead. Let's see if anyone has any last questions before we go. A little further away from my screen than normal. Well, I don't see a whole lot. That must mean that I did a fantastic job explaining rocket scientists to you all. And I hope that we have a whole bunch of future rocket scientists, maybe future NASA, future SpaceX, future engineers on our hand who are going to help bring people back to space, back to the moon and onto Mars. And who knows, maybe in your lifetime, even further. So let us know in the chat what you thought. We hope we'll see you back here tomorrow because Paulette will be here with another really exciting virtual planetarium program. And if you have questions specifically about NASA and their rocket designs, she's a great resource to help you guys answer those. So we hope we'll see you back here tomorrow at 2:30 p.m. Eastern. Otherwise, I hope you guys have a great rest of your day